Hi everyone, my name is Cesar Santoyo and I'm presenting our work titled Interval-Valued Markov Chain Abstraction of Stochastic Systems Using Barrier Functions. This work was a collaboration with the main author Maxence Dutrex, our lab mate Matthew Abate, and our research advisor Professor Sam Coogan. This work is concerned with the study of stochastic systems. A system is said to be stochastic when the evolution of its state and time is affected by some form of noise, which prevents the exact prediction of the system's state in the future. Examples are found in robotics applications where robots may be subject to both internal noise, such as sensor noise and actuator noise, and external noise caused by the environment, as in underwater robotics. Other examples are macroscopic social and network systems with stochastic supply and demand patterns, such as traffic networks, financial markets, and urban water systems. Some natural processes are also stochastic, which include weather events, neuron firing rates, and so on and so forth. Therefore, it is necessary to understand how to model, analyze, and interact with these systems. The problem of verifying whether a system possesses a given property is usually called the verification problem, and the problem of designing a control policy for achieving a given performance objective is known as the controller synthesis problem. In the recent literature, a lot of effort has been dedicated to the development of techniques for tackling these two problems in a stochastic framework for the class of so-called temporal logic objectives. Temporal logic objectives refer to well-defined sequences of states you would like a given system to reach or avoid in time, and include safety objectives, reachability objectives, repeated reachability objectives, among others. Solving these problems exactly for continuous domain systems turns out to be infeasible in general, and one has to resort to approximation methods instead. This is typically done by partitioning the continuous domain of the system into a finite number of discrete states and by generating an imperfect but simplified finite state representation of the original dynamics in the form of a probabilistic finite state transition system for this domain partition. Finally, by performing verification or synthesis on the finite state abstraction, we're able to obtain bounded error, probabilistic guarantees, and control policies with respect to the original continuous states. In this representation, stochastic systems are assumed to evolve in discrete time. That is, the state of the system only has well-defined values at discrete instances of time, as captured by this stochastic difference equation. Now, our paper is primarily focused on the abstraction procedure itself. How can we represent a continuous domain stochastic system with a finite number of discrete states? Recent works have shown the potential of so-called interval Markov chains, otherwise known as IMCs, for abstracting discrete time stochastic systems. IMCs are defined similarly to standard Markov chains, with the key difference that the probability of transition between any two states is given as an interval of probability instead of being just a single number. Using IMCs as abstractions is intuitive because if you take any two continuous states inside a given discrete region, let's say Q0, in this example, their probability of making a transition to another region, Q1, Q2, Q3, is likely to be different under the dynamics of our system. The intervals represent bounds on the probability of any continuous state within Q0 transitioning into Q1, Q2, or Q3. The state of an IMC evolves as follows. Every time a new state is visited, let's take Q0 here, a probability distribution respecting the intervals is chosen non-deterministically and sampled to perform the next transition. Techniques for analyzing IMCs are found in the reference papers below. Now, the next question is, how do we compute these bounds on the transition probabilities that we just discussed between any two discrete regions of the state space to generate an IMC abstraction? It turns out this problem is not easy to solve for general dynamics. Recent papers developed efficient IMC abstraction algorithms for the class of affine and disturbance linear systems and affine and disturbance mixed monotone systems. In our paper, we address this problem for the class of polynomial systems. That is, each component of the state map F is polynomial in the state X and the random disturbance W. Therefore, the main problem statement of our work is the following. Given a partition P of the domain D of the system, how does one compute correct and non-trivial bounds, that is, not ranging from 1 to 0 for all transitions, on the transition probabilities between any two discrete regions of P when F is a polynomial function? Note that being able to solve this problem also allows us to construct abstractions for finite mode stochastic systems of this form. if each mode of the system maps to polynomial dynamics. In this case, we can build an IMC abstraction for each mode of the system from a domain partition, which is equivalent to the so-called bounded parameter Markov decision process, otherwise known as a BMDP abstraction. This type of abstraction can be used to design mode switching policies and achieves a desired performance objective in the original system. So consider two discrete states Qi and Qj of a domain partition. Our goal here is to calculate an upper bound on the probability of transitioning from any continuous state in Qi to Qj in one time step. This is denoted by rho hat Qj. And to compute an upper bound on the probability of transitioning from Qi to the region outside of Qj in one time step denoted by rho hat x minus Qj. These bounds naturally yield an interval on the probability of transitioning from any continuous state in Qi to Qj, which can be used for our IMC abstraction. An upper bound on the transition from Qi to Qj is directly rho hat Qj. A lower bound on the transition from Qi to Qj is equal to 1 minus rho hat x minus Qj. To compute these bounds, we first need to introduce the concept of stochastic barrier functions. Stochastic barrier functions are tools which are used to provide probabilistic guarantees with respect to a stochastic process in a Lyapunov-like manner, that is, without any explicit computations of trajectories or reachable sets. In particular, by finding a barrier function satisfying certain value constraints on sets when evaluated against a stochastic process, one can determine an upper bound on the probability for the process to reach any given region of the state space from some set of initial conditions. Stochastic barrier functions have been established for both discrete time and continuous time systems, and for both finite time and infinite time horizon processes. For our specification abstraction problem, we are only interested in one time step guarantees for discrete time systems. For discrete time stochastic processes over one time step, the stochastic barrier functions equations are greatly simplified and are as follows. If there exists a function b of x satisfying these value constraints on a domain x and a target set x1, as well as an expectation constraint against the stochastic process of interest on a set of initial states x0, then the probability for the process to end up in x1 for any continuous state in x0 is upper bounded by this alpha term. So here x0 would be our previous Qi state, x1 would either be Qj or the complement of Qj. It's worthwhile noting that these equations follow directly from Markov's inequality. Now, to obtain bounds which are as tight as possible, the objective is to search for a small alpha value such that the function b of x satisfying these conditions exists. This problem can be cast as a so-called sum of squares optimization program of this form, where the set sigma represents a set of all SOS polynomials. A polynomial is SOS if it can be written as a finite sum of polynomials squared and is therefore positive for all x. So in the constraints of the optimization program, we want this term to be SOS, this term to be SOS, and so forth. And by assuming the function b of x to be a polynomial, and by having the s functions being positive polynomials over the subscripted sets, and by having the f function term be a polynomial, it was shown that this optimization problem over the coefficients of all the polynomials involved can be converted to a semi-definite program and is therefore convex. A tool for converting SOS programs to STPs is SOS tools, which we can use in the case study presented further. The fact that f is a polynomial comes into play in this expectation term, which expands into a polynomial since b of x is a polynomial whose coefficients are a function of the moments of the noise terms. The degree of the different polynomials involved in the optimization program is a hyperparameter, with higher degrees usually yielding tighter probability bounds at the cost of higher computational complexity. So the takeaway is that for polynomial systems, bounds on the probability of transition between any two discrete states of a domain partition can be computed by solving two convex optimization problems of this form. Finally, we need to figure out an efficient way to compute these polynomial representations for the regions denoted as x, x0, and x1. It is common to construct domain partitions where all states are rectangular. Therefore, we need to construct type polynomials which are positive for all states inside a rectangle Qi and for all states outside the rectangle to represent its complement so as to encode the set constraints from the previous slides. To do that, we derive the following polynomial expressions which under-approximate the unit square with greater precision, as well as over-approximate the unit square as the value t increases. Note that the negative of the under-approximation gives you an over-approximation for the states outside of Qi. Then we can approximate any arbitrary rectangle by shifting and scaling these polynomials appropriately. Here's a schematic summarizing the abstraction procedure. First, a partition of the continuous domain is constructed. Second, a polynomial over-approximation of each discrete region of the partition and their complement is computed. We showed how to do this for hyperrectangular states. Third, each ordered pair of discrete states, we solve a convex program to compute correct and non-trivial bounds on the transition probability under the stochastic dynamics of interest to generate an IMC or BMDP abstraction of the system, which can be fed into a verification and synthesis algorithm for interval-based abstractions. Now I'm going to show the applicability of our abstraction procedure in a verification numerical example. Consider the following 2D stochastic polynomial system evolving on this domain and subject to the following Gaussian noise. Although the system is not robustly forward invariant, the probability of transitioning outside of D is negligible and we assume it to be 0. We have the following probabilistic specification. We want the set of initial states of D from which the probability of satisfying this temporal logic specification is greater than 0.82. In natural language, this specification translates to never reach a B state and either reach a C state eventually or reach an A state within 2 time steps. The state labels are shown below. Here's our chosen domain partition with 160 rectangular states. We applied our abstraction procedure to generate an IMC abstraction of the system and performed verification using techniques from our previously cited work. We see that thanks to the abstraction verification procedure, we were able to determine some regions of continuous states satisfying the specification in green, and some regions that do not satisfy the specification in red. Due to the conservatism introduced by the abstraction, we see that some regions are undecided with respect to the specification, and a refinement of the partition would be required to achieve a smaller area of yellow states. We refer anyone interested in refinement to our previously cited paper. The total runtime of verification was 14 hours. Most of it was spent constructing the IMC abstraction. Although this runtime can be a bit discouraging, we believe that it can be greatly reduced with specialized high-performance coding for the SOS program and fully parallelized implementations. Importantly, we use only 2 cores for 25,000 bound computations, which are entirely parallelizable. In other words, there's no need to know a given bound to be able to compute another one. Therefore, we believe a specialized parallel coding architecture using GPUs, for example, could dramatically reduce the runtime. Finally, we also included a synthesis case study in our paper. We have a polynomial system similar to the one in the verification case study, but now the system has 2 modes corresponding to 2 different coefficients, AI and BI. The domain noise and state labels are identical, and now the objective is to find a mode switching policy that minimizes the probability of satisfying the same temporal logic as before. That is, for each state of the domain D, we want to select the mode which minimizes the probability that the subsequent transition of the system satisfies this temporal logic specification. By applying our abstraction technique on the same partition as in the verification example for each mode of the system, we were able to construct a BMDP abstraction of the dynamics. And by using the synthesis algorithm for BMDPs from our previously cited work, we found the most advantageous mode for all discrete regions of the partition with respect to our minimization objective. In conclusion, the key takeaways are we design an IMC BMDP abstraction technique for discrete time polynomial stochastic systems which yield correct and non-trivial transition bounds. These bounds are found by computing 2 stochastic barrier functions per transition in the system domain partition. We formulate the search for stochastic barrier functions as convex semi-definite programs. We demonstrate the application of our abstraction technique in a verification and a synthesis case study. Thank you.